Today's topic is geometrical optics. To start with, let's see a very simple case of refraction. You have a glass slab, an incident light strikes on it. This is a normal. If there is no media, it would have gone straight like this. But since, let's say this is air, this is glass, and this has a refractive index of 2. Air has a refractive index of μ1. Again, it comes out of glass. Again, it is here μ1. So when it strikes this air glass interface, instead of going straight, it bends towards normal. So this angle of incidence is called I. This angle is called R, angle of refraction. Now, sine I over sine R is given as velocity v1, v2. This is velocity of light in media 1. This is velocity of light in media 2. This is also called media 1. This is media 2. Okay. Now sine I or sine R, which was v1 or v2, can also be written as μ2 by μ1. So if you cross multiply, you will see sine I into μ1 is equal to sine R by μ2. Or we can also say sine in media 1 into μ1 is equal to sine R or sine R in media 2 into μ2. Or we can also write sine of theta 1 μ1 theta 1 and theta 2 are the angle of incidence and refraction in their respective area. This is called Slants Law. Now, many times you must have noticed that if you put coin in a tumbler, in a glass or a beaker and fill it up with water, the coin seems to become closer to you, meaning thereby it seems as if the coin has risen up from the bottom, right? So let us examine this phenomenon. Here we have an interface of glass and water, and we are going to see through air, sorry, glass and air. We are going to see through air, and if the object is here, and if we are seeing from air, what happens is the ray which originates from in a denser media, when it comes to a rarer medium, it goes away from the normal, and it looks as if this ray is coming from here and not from here, it is coming from here. So what we see is, we see this much distance, this much depth, whereas the actual depth is so much. So there is a change in depth, which is delta t so much. This is the change in depth. So let's write down some equations, and the equation is apparent depth divided by real depth. This is our apparent depth, whereas this is our real depth. So this is equal to mu2 by mu1. This is our formula. And you have to be careful that this is for viewing from mu2. It doesn't matter whether mu2 is rarer or denser. We'll take the case, just now we'll take the case which is opposite to it. Now let us take this case. In this case, the observer, this is an interface between air and glass. Glass is a denser media compared to air, and the observer is in the denser media. As against earlier the observer was in rarer medium. Here the observer is in the denser medium. Now what happens is, a ray of light which starts from the rarer medium would have gone like this, but because it encounters a denser media, it bends towards normal. So this is our angle of incidence, and this is our angle of refraction. Now in this case, the same formula will apply. Here mu2 will be for glass and mu1 will be for air, because in this case also we are viewing the object from mu2. Now using this formula, this immediately boils down to change in depth is equal to again, mind it, you are viewing from mu2. Now, if mu2 happens to be greater than mu1, what will happen? This will be, let's take a typical case of glass and air. Glass is about 1.3 to 1.4. Let's take 1.3. air is normally 1. So so it will be 0.3 times the thickness of the media. Thickness of, what is the thickness of the media? Thickness of the media is the thickness of media. This is the thickness of media. This will be minus. Now, if we come back to our this equation here, if we are always viewing from U2, and if the media from where we are viewing, whose refractive index is less than the one where the object is, then what happens is apparent over real will be less than 1, because this is less than this, which implies that apparent depth is less than real depth. So the object to us looks nearer to the observer than it is actually is. Now take the other case where apparent over real, where this one is more than this one. For example, which is the case of this one, when we are observing from glass. When we are observing from glass a depth in air, then what happens is mu2 is greater than mu1. So this is going to be greater than 1, which means apparent depth is greater than real depth. Which is the case here. Our object is actually lying here, but because of this phenomena, it appears here. So in this case, the object seems to be farther away from the observer. So it basically depends upon the ratio of whether mu2 is greater or mu1 is greater. If you are viewing from rarer media, then the object will appear closer to you. If you are looking from a denser media, the object will look farther from you, farther away from you. Now again, we take case of this is, let us say, air. This is glass. This is an incidence ray, originates in glass, not Japanese. Instead of going like this, it is air, rarer media, so it bends away from normal. This is our angle of incidence, and this is our refractive angle. Now what happens if you increase this angle? The refracted ray will be like this. If you further increase angle of incidence, a situation will come when the refracted ray is just above the axis, this axis, and at some angle of I our refracted ray becomes parallel to this axis. This is our R. And if we increase the angle of incidence further, what is going to happen? There will not be any refraction. Instead, the ray will come like this, as if it is bouncing off a mirror. So a situation where your refracted angle just becomes 90, for that the incidence angle is called critical angle. So what is critical angle? Critical angle is an angle of incidence for which R becomes 90 degrees. Right? Now if we write in terms of sin I, sin R, at situation when I becomes critical, we denote it as this thing. And at that time, R is 90 degrees, which is equal to now we are taking a case of air and glass. So sin theta critical can also be written as 1 over mu of glass with respect to air. Or we can also write mu of air divided by mu of glass. When we do with respect to this, then automatically we are making one entity as one, because we are saying with respect to. So there could be any other media. It's not necessary that you have to take glass or air. It could be any other media, which could be mu2, and some rarer media, which could be, let us say, mu1. Then we can always say sin theta critical will be mu2 by mu1. Obviously, mu2 has to be greater than mu1. This phenomena of total internal reflection has immense commercial use. For example, in fiber optics, what happens is the material, this material and the cladding this is, let us say, mu2, and refractive index of this material is mu1. Now, if we hit an instance light ray in such a way that this is more than our critical angle, so what will happen? A ray will go like this, and instead of refracting, it will come back. Again, same thing will happen. So it keeps happening. The light ray never escapes from the cable. Instead, it keeps reflecting over and over again and progresses this way. This is on account of total internal reflection. Next topic is prism. What is a prism? Prism is a triangular transparent body this is the front portion, this is the back portion. This front portion is parallel to this back portion. And if we see the front portion of it, it looks something like this. Now here, a ray of light strikes here. After refraction, it bends, takes this path. And after coming out of this phase, it refracts again into a rarer medium. So it takes this path. Now, the media from where the ray of light enters the prism is mu1. The refractive index of the media itself is mu2. And after exiting from prism, it goes back to media 1. Right? Now, if there was nothing in between, this ray would have gone straight out. But because of this prism, it took two bends. One is this one and another is this one. So effectively, the ray which would have gone like this has now gone in this direction. So what is the angle between them? The angle between them is this. We call that the incident ray has deviated by this much angle after exiting from prism. All right. Let's do some treatment. We call this as angle A. This is angle R1, angle of refraction for this incidence ray. And this is the angle of refraction for this incidence ray which emerges out of the air. Okay. And let's call this as P, angle P. So if I write the equation only in terms of angle, and so angle A, which is this one, plus angle P, which is this one, is equal to 180. Why is it 180? Because this angle is 90 and so is this angle 90. So if we talk about this quadrilateral A, Q, P, this P, and R, this R, is a quadrilateral whose internal angles are 360. So 90 plus 90 is taken out by these two angles. So what is remaining is 180. That's why A plus P is 180. Now, this angle R1 plus this angle R2 plus angle P. These three angles are angle of a triangle whose sum will be 180. So we can write R1, R2 plus P is 180. If we look at these two equations, it means that A is equal to R1 plus R2. Yeah. Now, if we see this angle delta, this delta is an external angle to this particular triangle. If I elaborate this, this is our Q, this is our R, this is our delta. So delta is an external angle to this triangle. So we can write delta is equal to I minus R1. This whole was R1. This whole was I. If you subtract R1, you will get this angle. This angle is nothing but I minus R1. Similarly, the second angle, this angle will be what? This is plus, we call it I dash. This whole angle is I dash, out of which we take out R2 and we get this angle. So this is I dash minus R2 or it is equal to minus R1 plus R2, right? And we know if we substitute R1 plus R2 as A, this becomes or delta is equal to I now, if you see that when this delta will be minimum, now when will this delta be minimum? This is fixed. The only variable is incidence angle, which is entering the prism, and this is the exit angle. When I1 and I2 are I dash is same, then this delta will be minimum. So the condition for delta minimum is I is equal to I dash. Now, if this happens, in that case, this also implies that our R1 will be equal to R2 also. All right. Now, our now if we write mu2 over mu1, which is this is mu2, this is mu1, then this is equal to sine of incidence angle in mu1 divided by sine of incidence angle in refracted angle in mu2, this one. R1. Now, since R1 and R2 are same, we can call it as R. And I we have seen is what? Delta minimum is equal to 2I minus A implies I is equal to delta minimum plus A by 2. Similarly, R1 plus R2 is this thing. Since R1 and R2 are same, we can also write A is equal to R plus R, or R is equal to A by 2. So R is equal to A by 2. We substitute these values here. So what we get is mu2 minus mu1 is equal to sine of I. Sine of I is this much. This is our final equation. Okay. Now, few conventions in mu. When we write mu of A with respect to B, we can reverse the equation also. If we take mu of B with respect to A, if we invert this mu, we will get B with respect to A. And the third relationship is, if you have mu of A with respect to B, if you multiply with mu of B with respect to C, what you will get is mu of A respect to C. Next thing is that we study refraction at spherical surfaces. Earlier we have seen all these treatments at plane surface. This surface was plane, this surface was plane. Again, when we talk about total internal reflection, this surface was plane. But what if the surface is not plane? The surface is spherical. Let's say we have a sphere of glass, for argument's sake, of a refractive index mu2, and we are in air. Then what happens is, if this is an object lying here, ray goes like this. This is the normal which passes through the center of curvature. Then it would have gone straight, but because this is a denser media, comes here, strike this and forms an image here. Now this is center of curvature, which is R, also called radius. Object is kept here, so this distance is U. An image is formed here, so this distance is V. and we have refractive index here is mu1. Here refractive index is mu2. So our formula is mu2 over V minus mu1 and mu2 we have already seen. This is mu1, this is mu2. This distance is V and this distance is U. R is radius of curvature, which is this much. So this becomes our formula. And mind it, in all this formula, the sign convention is always applicable, is to be applied. I'll talk about sign conventions separately, but let's get over with the main topics. Now we had seen that there was only one spherical surface like this. What if there are two spherical surfaces? Like in a lens, you have one spherical surface like this. That means this is part of one sphere and this surface is part of another sphere. Both can have different radius. Not necessarily they have to be same. So let us take this is a case of double convex lens, for example. This is, let us say, here, same mu, and mu of this material, let us say glass or whatever, is mu2. This surface has a radius of curvature r1, this one. This surface has a radius of curvature r2, and this is their respective C. This will be C for this surface. This C will be for this surface. We have an object here. If we place an object here, a ray goes like this, gets refracted, comes here, and we have another ray coming this way. So what we get is an image here. In this case, the relationship comes out as like this. What is this? This is the focal length of this lens. Mu1 and mu2 are this one and this one. R1 and R2 are the respective radius of curvature of two spherical surfaces. So we are not going to the derivation part of it, but as a relationship, we can see that 1 over f, 1 over focal length of this lens is equal to ratios of the refractive indexes minus 1 multiplied by inverse difference of inverse of their radius of curvatures. For lenses, our formula is this is the focal length of the lens distance from pole to object. This is distance from pole to image. Now, if we see a ray diagram of a typical lens, this is our lens. We place an object here. This is object, and this is the image that is formed. So f will be focal length of this lens. This is our object. So this distance will be u. This is our image formed, this one. So this will be v. And this formula will be applicable. Now we have to be very careful that we have to use it with, we cannot use it simply v is v, u is u. We have to use sign convention. Now I will slightly delve into what is a sign convention. The convention is that all the distances, whether it is u, v, f or whatever, is to be taken from the pole. Pole means this portion. If you're talking about object distance, position of object from pole. Similarly, image, if image is formed here, distance of pole, distance from pole to image. So all distances are to be taken from pole of the lens. We're first talking about lens. If it is a mirror, it is case of mirror. Now, we cannot take any distance just like a geometrical distance. No, we have to take distance as per sign convention of optics, and which is the direction incident ray is taken as positive, meaning thereby all the distances from pole, if you go in the direction of incident ray, then it will be positive. And if you have to take any distance from pole in direction opposite to the direction of incidence ray, then that distance will be negative. For example, here the ray is going like this, and if we take u, for u we have to travel back in this direction, which is opposite to the direction of our incidence ray. So our u will be negative. What about V object? Now the object is formed here, and we have to take the distance of object from pole. This is pole, and we are going in this direction, which is the direction of our incidence light. So our V is positive. Now what is left is F. Okay. Focal length of convex lens and convex mirror shall be taken as positive. If we talk about only of lenses, convex lens, F is positive. Concave lens, F is negative. This is convention. And similarly, all distances, if we take height of this object, we are going in this direction. This will be positive. And if, let us say, our image is formed below the principal axis, we are going to take the distance from principal axis down. This will be negative distance. So these are the conventions. We saw the refraction from two spherical surfaces where different radii are involved. This formula is also called lens maker's formula. Because you can achieve a particular focal length you can achieve same F by making different combination of R1 and R2s. So this formula is extensively used by people who manufacture lenses. So it's called lens maker's formula. Now in case of lenses, we come across a term called lateral magnification. For example, if we take our lens, take our object like this, and this is the image that we're going to get. Then we want to know if this is of height h1, the object, or ho, what is the height of our image? Obviously, more the height of h1 compared to h0 will say that this image is magnified. So we define a term called lateral magnification as size of image over size of object. Or if we see these triangles, these two triangles are similar. The heights are proportional to U and V. Now, what is power of a lens? You must have seen, if you take a lens and if you can focus it on an object very closely compared to another one, which focuses at a distance, the one which focuses nearer is more powerful. Why? Because power of a lens is defined as reverse of focal length in meters. For example, if focal length of a lens is 20 centimeters, then its power will not be 1/20, but units in meters, which will be 0.2 or, and the units of power are diopters, or we simply, in short, we write 5D. Now, what happens when we combine lenses? Let's say we have one lens here. This is one lens. This is another lens. If we combine them, then what is the equivalent of equivalent? Focal length of this combined lens. We put our object here. An incidence ray goes like this. Then it tends to emerge like this. It would have emerged like this, but because of refraction, it goes like this, and we get our image here. The ray here would have gone like this had there been no second lens. What this lens does is picks up this one as the object and makes an image here. So if we say that this lens has a power P1, this lens has a power P2, then this is equal to F1 plus, and if we say this is an equivalent F is the equivalent focal length of combined lenses. So this is the formula for finding focal length of a combination of lenses. Similarly, on the same analogy, the power of final equivalent lens will be equal to sum of the power of individual lenses. These are the two lenses, they combine to make a one lens whose equivalent power is this. Power of lens 2. This is power of lens 1. This is the combined power of lens 1 plus lens 2. Now, is it necessary that these lenses have to be put together? No, you can have lenses which are separated. Okay. So how does that treatment look like? Let's say you have one lens here, you have another lens here. This is having a power P1. This is power P2. And let us say they are separated by a distance D. And this is the place where this is the place of equivalent lens of these two will supposed to be. Say this is focal length, this is focal length 2. Then focal length of the combined lens will be defined as, earlier we just said 1 over f1 plus 1 over f2. This was the case when there was no distance between they were kept together. But when they are separated, another term comes in, which is d by. This is the formula for which gives the equivalent focal length. But which is the place for equivalent lens? Let's say the equivalent lens looks to be here. Then this distance z is defined as if we take f1 as this lens, then we will take distance from the other lens. And you can reverse it also. Here also sign convention will be applicable. Now I'll quickly run you through various ray diagrams. This is our lens. If the rays are coming from infinity, they will all converge at focal point. The object is at infinity. Image will be formed at a focus. It will be small, it will be real and inverted. Secondly, if it is beyond 2f, if we have an object beyond 2f, the image is formed here. This is when the object is between infinity and 2f. The image will be formed between f and 2f. The image will be formed somewhere in this region. And size will be diminished and image will be inverted, but diminished, inverted, but it will be real. Third case is when object is placed as 2f. If it is placed at 2f, image will also will appear at 2f. Object is 2f, image is also 2f. The size will be exactly same as size of object. Image will be same as size of object. Image will be real and it will be inverted. If we take our object between f and 2f, this is f between in this region, then the image is formed beyond 2f and infinity. And you can see this is the image will be magnified, it is real and it is inverted. What if our object is at focal point? If it is at focal point, all the rays emerging becomes parallel. So if an object is at infinity, image will be formed at infinity. It will be magnified because at infinity the two rays parallel will appear to make a huge image. It's going to be real and inverted. Next case is if our object is between pole and F. This is our pole and this is our F. If it is in this region, this is the object. this is the image which is formed. Image will be formed between anything between 0 to infinity, depending upon how close. This could be here, the object could be here, 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 wherever. Depending upon that, the image will, this image can vary from as close as this to as far as this. So it will go from 0 to infinity. It will be magnified, but it will be virtual. Whether it is closer or whether it is far, the image will be virtual and invert, and it will be erect. It will not be inverted, it will be erect. Now, taking case of concave lens, if the rays are coming from infinity, they'll focus, they appear to be coming from this focal point. They are diverging like this. Since the rays are diverging, this is also called diverging lens. In this case, we saw that the rays were converging. So this convex lens is also called converging lens. Next, if our object is at between infinity and 2f, then the image will be formed at between pole and f. This is the pole. It will be formed in this region. Size of the image will be small and it will be virtual, because if you look at from this place, the ray appears to come from here. It will be erect. So this and these cases are very similar to each other. This is when our object is at 2f, or in this case our object is at f. Or in this case our object is between pole and focus. Now we have studied lenses. Now we will study mirrors. Spherical mirrors. Plane mirror we see every day. Looking mirror, looking glass. Now again there are two categories, concave or convex. If this is our mirror and the silver is on this side, this is called concave mirror. On the other hand, if the silvering is on this side, we call this as convex mirror. Now again, the convention here, the mirror formula is did you notice something here? In case of lens, this sign was negative, but in case of mirror, in the formula, this sign is positive. Another difference is in case of lenses, magnification was defined as V over U. But in case of mirrors, magnification is defined as minus V by U. Here again, the conventions are same. Conventions are same as lenses. That means rays in the direction of incidence ray, if we take the distance, will be positive. And if we have to, while taking the distance, if we have to go in a direction opposite to the direction of ray of incidence, then the distance will be negative. Now this is a concave mirror. First case is rays are coming from infinity. They will focus at focal point. So object is at infinity. Image will be formed at focus. It will be very, very small. In fact, it will be point image. It will be real and inverted. Second case is, instead of being at infinity, we bring it closer between 2f and infinity. The image formed will be at f and 2f in this region. The image will still be diminished. It will be real and inverted. Third is, if we bring our object exactly at 2f, this is 2f position. The image is formed exactly at the same place, but in the opposite direction. So it is formed at 2f, same size as object. It is real, image is real, and image is inverted. We bring our object closer. This was at exactly 2f, so we bring it closer to f. Between f and 2f, if your object is between f and 2f, then our image is formed beyond 2f. This is our 2f. It will be formed beyond 2f. And in this case, it will be magnified. Image will be real and image will be inverted. Now, what if our object is exactly at infinity as at focal point? The refracted rays become parallel and we will get image at infinity, which will be hugely magnified. It will be real and inverted. We still come closer, and we come closer between pole and f, or 0 and f. Then what happens is, our image is no longer real, it becomes virtual and erect. At the same time, it gets magnified. Okay. What happens in case of convex mirrors? If rays are coming from infinity, they appear to have, they diverge like this, and they appear to come from this focal point. So if an object is at infinity, image is formed at focal point behind the mirror, which is virtual, erect, and highly diminished. In fact, it will be just point object, point image. If we come closer, if we bring our object closer, which is less than infinity, then our image will be formed between P and F, between pole and F. This is our pole and this is F in this region. But this is all behind the mirror. So it is all virtual. Image will be erect, but it will be diminished. So if we come any distance closer than this, the image will be formed between P and F only. and it will be all virtual direct anti-connection size. We will recap on certain areas which many times create confusion. Converging lens or mirrors. Converging lens is a convex lens and a converging mirror is concave mirror. Whereas a diverging lens will be a concave lens and a diverging mirror will be convex mirror. Magnification, lateral magnification is basically height of image divided by height of object. But the formula in case of lens and mirror are different. Sorry, this not this one. For lens, the magnification is plus V by U. For mirror, magnification is minus V by U. For mirror, okay, we have already seen this, same thing. Now, many times you will hear the term rarer medium or denser medium. What is rarer medium or denser medium? A rarer medium is where refractive index is less. And what is a denser media? Where refractive index is more. What is a prism angle? We have seen prism. Prism angle can be this, but how do you define which is the prism angle? Prism angle is the angle between the incident, the face, the angle between the faces of a prism on which on one surface the rays is coming into the prism as incidence rays, and another phase is where it is emerging out. This one. So the phases involved in getting the rays in and getting the rays out, that angle is called angle of prism, normally denoted as A. Now, in case of lens, the formula is this is in case of lens. In case of mirror, this formula is this is for mirror.